Good afternoon, dear ladies and gentlemen, and today we would like to talk about nanobiotechnology for neurological disorders. But as we dive in, we would like to focus on the nanotechnology for treatment of the neurological disorders. And let's start with a world. Imagine a world where over 3 billion people are affected by brain diseases. Unfortunately, this isn't a far-off possibility, it's our current reality in 2024. Neurodegenerative disorders like Alzheimer's and Parkinson's disease impact millions worldwide, leading to devastating losses in cognitive and motor abilities. These conditions don't just affect patients and families, but also place a massive burden on healthcare systems globally. The statistics speak for themselves. Alzheimer's disease prevalence has doubled in the elderly population over the last 20 years, while Parkinson's disease cases have increased 2.3 times. These diseases are primarily managed by treatments that address symptoms without effectively slowing or halting disease progression. In 2020 alone, the healthcare costs associated with Alzheimer's disease were estimated at an astounding of 305 billion, and the Parkinson's disease costs reaching 51.9 billion. Additionally, most therapeutic agents developed over the past 15 years have failed to meet efficiency endpoints in large-scale phase 3 clinical trials, underscoring the difficulty of finding effective treatments. Today, we'll explore the potential of nanotechnology or nanobiotechnology as a revolutionary approach to these challenges. But let's first look at these diseases in more detail to understand what makes them so complex and difficult to treat. Neurodegenerative disorders are characterized by progressive loss of neuron structure and function, leading to significant declines in cognitive and motor abilities. In Alzheimer's disease, individuals may initially struggle with memory lapses, like forgetting names or daily tasks, but the condition progresses to severe memory loss and difficulty in recognizing familiar places or people. It's often called the disease of forgetting, because it gradually erodes a person's memories and identity. This deterioration affects brain functions broadly, starting with memory and ultimately impairing the ability to perform daily activities. In Parkinson's disease, the primary impact is on movement. The brain experiences a decrease in dopamine, a neurotransmitter essential for smooth and controlled motion. This deficiency causes symptoms such as tremors, stiffness, and balance difficulties, which can significantly affect the person's mobility and quality of life. With these disorders significantly impact patients' lives, developing effective treatment remains a major challenge, largely due to the protective yet restrictive blood-brain barrier. Blood-brain barrier is a highly selective and protective barrier that separates the circulating blood from the brain's extracellular fluid, the fluid surrounding brain cells, in the central nervous system. It's primarily made up of tightly packed endothelial cells, astrocytes, endocytes, and pericytes. Together, these components restrict the passage of substances from the bloodstream entering the brain. This selectivity is crucial for maintaining a stable environment essential for proper brain functioning, but it also poses a significant challenge for drug delivery. Approximately 98% of small molecule drugs and nearly all large molecule drugs are unable to cross the blood-brain barrier. The blood-brain barrier impermeability is due to several factors. Tight junctions prevent substances from slipping through gaps. Efflux transporters block unwanted molecules, and a lack of fenestrations prevents passive diffusion of substances into the brain. The selective nature of the blood-brain barrier makes it extremely difficult for many therapeutic agents to reach the brain. However, nanoparticles with their unique properties offer a promising solution to overcome this barrier and enable effective treatment to neurological disorders. What are the nanoparticles? Nanoparticles are structures with dimensions between 1 to 100 nanometer. At this small scale, they exhibit unique properties such as increased reactivity, enhanced surface energy, and altered optical characteristics. These properties arise because nanoparticles have larger surface area relative to their volume, with surface atoms being more reactive and able to interact effectively with biological systems. Nanoparticles have emerged as a promising strategy to overcome the blood-brain barrier instinctive nature. Several biological mechanisms facilitate nanoparticles crossing the blood-brain barrier. And the first, carrier-mediated transport. Nanoparticles can be functionalized with ligands that mimic natural substrates of transport proteins on the blood-brain barrier, such as glucose or transferrin, allowing them to be transported across via these carriers. Adoptive-mediated transcytosis. Positively charged nanoparticles can interact with the negatively charged cell membranes of endothelial cells, promoting their uptake through the blood-brain barrier. Receptor-mediated transcytosis. Nanoparticles can be engineered to bind to a specific receptor on the blood-brain barrier, such as low-density lipoprotein receptors or insulin receptors, facilitating their transport across the barrier. These mechanisms highlight the versatility of nanoparticles in drug delivery systems, aimed at treating neurological disorders by effectively penetrating the blood-brain barrier while minimizing off-target effects. Now that we have explored the various mechanisms by which nanoparticles can cross the blood-brain barrier, let's take a closer look at three distinct types of nanoparticles and how are they being utilized in research to tackle neurodegenerative diseases. First and foremost, what are polymeric nanoparticles? Polymeric nanoparticles are among the most widely researched nanocarriers for drug delivery, especially in the context of neurodegenerative diseases. One of the most studied polymers is polylactic glycolic acid, or PLGA. Approved by the FDA in 1974, PLGA is prized for its biocompatibility and biodegradability. These features make it highly suitable for medical applications because PLGA degrades into lactic acid and glycolic acid, two compounds naturally metabolized by the body. PLGA nanoparticles can encapsulate therapeutic agents within their polymer matrix, creating a core shell structure. This design allows for controlled drug release, which is crucial for managing neurodegenerative conditions that require steady, prolonged exposure to therapeutic compounds. PLGA nanoparticles range in size from 10 to 1,000 nanometers, but those on the lower end of the scale, closer to 10 to 200 nanometers, are typically more effective at crossing the blood-brain barrier. How do PLGA nanoparticles penetrate the blood-brain barrier? PLGA nanoparticles can be modified with ligands or peptides that facilitate receptor-mediated transport across the blood-brain barrier. For example, conjugation with peptides like CRT enhances the ability to penetrate blood-brain barrier by targeting specific receptors such as the transferrin receptor. Once across the blood-brain barrier, PLGA nanoparticles can be internalized by brain cells through endocytosis. Modifications such as pegylation can enhance their diffusion within brain tissue, improving targeting efficiency. What are the applications of the PLGA? In Alzheimer's disease, PLGA nanoparticles are used to deliver drugs that mitigate oxidative stress and neuroinflammation, key pathological features of Alzheimer's disease. For instance, they can carry antioxidants to neutralize free radicals and reduce cellular damage, thereby slowing disease progression. Additionally, PLGA nanoparticles have been used to deliver inhibitors of amyloid beta aggregation and other neuroprotective agents like curcumin, which have shown efficacy in improving cognitive functions in Alzheimer's disease models. For Parkinson's disease, nanoparticles are used to encapsulate L-DOPA, a standard treatment for Parkinson's disease symptoms. The challenge with L-DOPA is its limited ability to cross the blood-brain barrier when administered orally. So, PLGA nanoparticles enhance its delivery directly to the brain, potentially increasing its efficiency by ensuring more consistent therapeutic levels at the target site. Moreover, PLGA nanoparticles can also aid in restoring lysosomal functions and mitochondrial membrane potential, addressing some underlying cellular dysfunctions associated with Parkinson's disease. What are the limitations of the PLGA? PLGA nanoparticles face certain limitations because they tend to have lower drug loading capacities, which means larger doses might be needed to achieve therapeutic effects. Furthermore, they sometimes experience an initial burst release, where a significant amount of the drug is released quickly before setting into a slower, sustained release. This can disrupt therapeutic effectiveness. Finally, although PLGA is biocompatible, its biodegradation or degradation products can, in some cases, produce localized immunogenicity, triggering mild immune responses in patients. The next, what are lipid nanoparticles? Lipid nanoparticles, also known as liposomes, are another highly effective platform for drug delivery. Discovered by Alec Banham in the 1960s, liposomes consist of phospholipid bilayers that form a spherical vesicle. This structure closely resembles the cellular membrane, which makes liposomes ideal for interacting with cells. Liposomes have an amphiphilic nature, meaning they contain both hydrophilic and hydrophobic regions. This allows them to encapsulate a broad range of drugs, whether water or fat soluble. Liposomes typically range from 50 to 450 nanometers and are highly biocompatible. They can cross the blood-brain barrier by various methods, including endocytosis, where brain endothelial cells absorb the liposomes directly. Surface modifications as the addition of transferrin or antibodies have been shown to improve their targeting efficiency by attaching cell-penetrating peptides, CPPs, to their surfaces. Liposomes can also enhance the delivery of drugs to specific brain regions. Applications in neurodegenerative disorders. For Alzheimer's disease, liposomal formulations are being explored to deliver compounds like curcumin, which has anti-inflammatory and antioxidant properties. Liposomes coated with cell-penetrating peptides have also been used to deliver drugs like rivastigmine, a cholinesterase inhibitor, intranasally to improve drug distribution in the brain. In Parkinson's disease, liposomes loaded with dopamine or dopamine analogs offer the potential for sustained release, which is beneficial given dopamine's short half-life in bloodstream. However, lipid nanoparticles come with their own set of challenges. Off-target accumulation, where liposomes are distributed to unintended areas, can lead to side effects. Additionally, some patients experience complement activation-related pseudoallergy, an immune reaction to liposomes that may cause mild to severe allergic responses. Last but not least, what are metal nanoparticles? Metal nanoparticles, especially those made from gold and silver, bring unique advantages due to their optical properties. Gold nanoparticles, for instance, exhibit surface plasmon resonance, a phenomenon where electrons on the metal surface resonate with specific wavelengths of light, and this can be exploited for both imaging and therapeutic agents. What are the applications in neurodegenerative disorders? Gold nanoparticles can interact with amyloid beta peptides, which are implicated in Alzheimer's disease. The surface chemistry of the gold nanoparticles can be tuned to enhance specific binding to AB peptides. This binding is primarily driven by electrostatic interaction, which reduces the propensity of amyloid beta monomers to form toxic oligomers and fibrils. By binding to AB or amyloid beta, gold nanoparticles can inhibit the formation of beta sheet structures that are characteristic for mature amyloid fibrils. This process potentially slows down the progression of Alzheimer's disease by preventing the aggregation of these peptides into neurotoxic forms. In Parkinson's disease, silver nanoparticles have shown potentially disrupting aggregates of misfolded alpha-synuclein proteins. These proteins contribute to neurodegeneration when they aggregate. Silver nanoparticles can adhere to the surface of bacterial cells and other proteins, altering membrane properties and potentially leading to cell death. This is achieved through mechanisms such as oxidative stress induction, disruption of intracellular organelles, and modulation of the signal transduction pathways. Prevention of aggregation. Silver nanoparticles can prevent biofilm formation by adhering to cell surfaces, which is crucial in fighting pathogenic microorganisms. This property is also beneficial in preventing the aggregation of proteins like alpha-synuclein. While promising, metal nanoparticles do raise concerns about biocompatibility. Long-term accumulation in the body could lead to toxicity, as the particles may not degrade as easily as polymeric or lipid-based nanoparticles. Research is ongoing to understand their safety profile and optimize their design for clinical use. In conclusion, the potential of nanobiotechnology to revolutionize the treatment of neurodegenerative diseases offered hope for millions affected by conditions like Alzheimer's and Parkinson's disease. Through nanoparticles, we can overcome the formidable challenges posed by the blood-brain barrier, enabling targeted and precise delivery of therapeutic agents directly to the brain. Polymeric nanoparticles, lipid-based nanoparticles, and metal nanoparticles each bring unique strengths to the table, offering new possibilities for drug delivery and disease management. While challenges remain, such as limitations in drug loading, potential immune responses, and long-term biocompatibility, continued research is essential to optimize these technologies. The hope is that as these technologies advance, we'll unlock more effective strategies for managing and even preventing these complex neurological diseases. In this journey, nanomedicine holds the promise of transforming the landscape of treatments, offering a brighter future for those affected by these debilitating conditions. And thank you so much. That is the end of our content regarding nanobiotechnology in neurological disorders. And here are the reference list that we have used to deliver the following presentation or the video. And all the illustrations were being done or have been used from the BioRender and Canva. Thank you for your attention.